Welcome back to Wood Engineering. I'm Jeff Arochko from Carleton University, and in this video, we are going to continue with part 3 of our epic beam column design example from birth to completion of designing a beam column from scratch. Okay, so in the last video, we managed to we started with our estimate of our eccentricity, E, which was 40 millimeters, and using that we could calculate some moments for this beam, and then we could go through and also calculate the shears and do all of the different load combinations and check all of the uplift cases and come out with basically governing loads for each individual load combination or load case. And we summarize those at the end here. So now that we have some more information, we are going to go ahead and try to, first of all, look at what the deflection criterion is, which is the only thing that we kind of haven't looked at yet. And also to go ahead and pick a trial section. And that will be the section that we go through and do all our full checks for moment, shear, compression, deflection, and then of course our beam column interaction. So let us get started. We are going to first take a look at what is going to be our minimum EI for deflection. Okay, so there's no explicit deflection criteria for wind columns. We have our beam criteria in the standard in chapter 5. But one recommended deflection criteria for wind columns is very similar to that deflection criterion from our standard, which is to minimize the inward deflection or outward deflection to L over 180. And in this case, since our L is 3000, our deflection criteria then is we want to stay under 16.7 millimeters or 17 millimeters. Okay, now we have two different things that are causing deflection here. One is the lateral load from the wind columns. I'm going to scoot all the way up back to the beginning. So this was our design case that we're looking at. One thing that's going to cause deflection, the primary thing that's going to cause deflection are these loads from the wind columns, which are going to cause our, from the wind mullions, which is going to cause our beam column to deflect inwards like that. On top of that, we have also some load that's coming, some deflection that's going to be caused by this vertical load acting at an eccentricity. Okay, so how are we going to calculate that? We are going to look at our load combinations and pick basically the worst one. Really, the primary thing that's happening here is these lateral loads are what's going to cause the most bending. This eccentricity is going to cause something very small. But we're going to basically look at the load combination that's going to cause bending in the same direction as this bulk lateral bending caused by the lateral loads. So that's going to be basically the uplift load. So our governing load combination for that is going to be the wind plus the dead. Okay, the dead we're not going to fully get rid of. Okay, so how do I find those deflections? I am going to lean on my structural analysis strengths and go to the tables in the standard. Okay, so for example, I am going to look at what's the deflection caused by just the lateral loads. Okay, and if I want to find the deflection for a situation like that, I can go to the standard. And for example, I can find here the situation for two equal concentrated loads placed at third points. This is in, not the standard, sorry, but the wood design manual. And you can see that we're given the deflection equation for that situation right here. So that's what I'm going to use. And I'm going to rearrange this equation to solve for my minimum EI. So the deflection So then if I rearrange that equation for EI to get a minimum EI, I'm going to get this, where W lat is the same as my P. So P is my lateral load, that 30 kilonewtons. And so I get 1,725 times 10 to the 9 Newton millimeters squared. And don't forget that this is using the unfactored loads. So what do we get for the effect of the vertical load times the eccentricity causing bending? We would use our table for serviceability limit states, which looks like this. And we're going to use, basically, it's the W that is the one that causes bending in the same direction as this bending. And we're going to see that the effect is small, so it's going to turn out that we don't have to check both. And we're going to use a 1.0 times dead. So 1.0 times dead plus 1.0 times W. We're not going to include the companion load because that's not going to cause bending in the same direction. And I have an equation for calculating that deflection. And so the applied load that we're interested in here is basically dead plus wind, and dead is 150, and wind is negative 100. So this is going to end up being 50, but downwards, which means that it's actually going to bend it in the opposite direction. So we have this situation here. We have this load bending like this. So we have a bending that is in this direction. And then from our dead load, we have an eccentric load here, right, which is going to actually cause bending like this. And that effect is going to be very small. You'd see if you calculate out what the deflection would be for something like that, it's going to be quite a bit smaller, like an order of magnitude or two smaller than the deflection caused by the lateral bending in this case. If we did look at the worst case of that, so let's look at the worst case, which would then be dead plus dead plus snow plus just dead plus snow, basically. So dead plus snow is 150 plus 200. These are unfactored loads, right, which is 350. And remember, the moment caused by that is going to be 350 times E, and E is 0.04 meters. So this is the load, P, this is our E. So we get a moment of 14 kilonewtons meters. And the deflection for that, okay, so this is basically looking at what's the deflection for a moment. And the equation here we can get from structural analysis. So we're going to get delta max equals, and I'm not going to go over exactly how we get this, but this is deflection for a single point moment at the top. Okay, so if I rearrange this for EI min, and the value we get is 484 times 10 to the 9 Newton millimeters squared. So this is the maximum bending in the outwards direction, like this kind of bending. Okay, so that is an order of magnitude, well, not quite, half an order of magnitude lower. So this is really the one that's going to govern, the one up here. That's the high strength that we're going to actually need. Okay, so that's my required IE min, 1725. If both of those were in the same direction, then then obviously I would need to add those EIs together. But here, since they're in opposite direction, like if they were in the same direction and for the same load combination, then I would add them together. But as we saw, there is only one load combination that provides bending in this direction. Okay. Great. So next step is we need to determine basically what our trial section is. And we are going to look at kind of all of the different moments and axial forces and shears and try to come up with a section that's going to work for all these cases, keeping in mind that I'm also going to have a combined axial load and moment effect. Okay, so we're going to go to those tables. We're going to find a section that works. Here, if we recall, are some of the higher PF and P and MF values. So this was the highest one for 88 kilonewtons. MF max was about 42. And VF max was around 48. Okay, so those are kind of our targets. And also our EI min that we just looked at is 1725 times 10 to the 9. Okay, so armed with all that, let's go to the tables and see what we can find. All right, so let's start with moment capacity and shear capacity and ESI. Okay, remember, we got to leave some excess moment capacity to keep to take account for the fact that sometimes our we have their combination equation. So we're going to try the combo equation as we go here. Okay, so here we have we need an MF of 42. So some of these are in the right range here. Okay, for MF of 42 if we go with an 80. But you see the VF is not big enough. We need a 48 here. Okay, so, and the ESI you can see is not going to be a problem because we have a requirement of 1725 times 10 to the 9, and all these are much, much larger than that. So we're not going to have a deflection problem here. Okay, so we need higher shear, and of course we don't want to target just exactly the moment capacity, which is 42. We want to be maybe, you know, double that to take into account the fact that we need to apply some axial compression to this beam as well. So maybe a beam like this, well, this one just barely reaches the VF. So this could potentially be a possibility depending on the axial capacity. But let's not forget as well that VF here, the VF that we're using here, doesn't take into account the fact that we're going to have a reduction. Well, I mean, the VF doesn't have to take into account anything, but when we look at the VRs to compare it against in the beam selection tables, they don't take into account the fact that we have a notch, right? So that compression side notch is going to reduce our strength by somewhere between, you know, 10 and 20% because we have a 20% notch. Okay, so that means if I go back to this, okay, so going right for that shear value is not, okay, so 80s don't look like they're really going to work. We could do a 130, and the shear that would work is probably one of these two. Okay, so that would be a 130 by 418 maybe. The moment value is high enough. It's about double what our moment, our factor moment is. So factor moment was 42. This is 87. It's about double that. Shear is 48. We have to take into account that there's a notch. So yeah, maybe 57 is okay. And this is our EI, which is 8150, and we need 1725. So that's more than okay. So that's one option. Although it is a pretty deep beam. It's 418. You'll see it's actually deeper than the beam that we assumed when we tried to calculate our E. Remember, we assumed that our E was based on a depth of 400. So it's going to look like a very imposing beam column. So let's pick one that's maybe a bit more compact. I'm going to come to the 175 wide glue lambs, And we can see here moment resistance of 62. Okay, so that might be kind of a bit close. We got 55.9, so that is greater than our 48. I think that should be enough to account for the notch. Our ESI is fine. And our MR is maybe going to be okay. We'll see, depending on how much axial load we have. So our MF here is 42, so 62, so we're using about 2/3 of it up. So depending on how it goes with the axial load capacity, this might be okay. The one below is probably not going to be okay because the VR is 49 and our VF is 48, and this VR doesn't account for the fact that we have to cut a notch. So this one is probably not going to be any good. So let's keep this one in mind, 175 by 304, and we'll go to the other table, which is in the combined loading section, if you remember. So if I look at remember chapter 2 is bending, that's where we were. Chapter 3 is compression. Chapter 4 is tension. Chapter 5 is combined loads. And in the combined load section, we have this table, which is a combined column selection table for glulam. And it doesn't have moment and axial capacity. What it does is it gives axial compression capacities for a bunch of glulam sections that are usually used as beams. So these are like axial capacities of beams. And this is the grade that we're talking about here, 20FEX. Okay, so we were in 175 by 304, which is not exactly on here. Okay, so you see for beam columns, it's assuming that you want a section that is a bit squarish, that you're probably not looking for one that is too deep. Otherwise, you wouldn't probably be designing a beam column. You might just be designing a beam. You know, beams tend to be deep, columns tend to be more squarish because of buckling efficiency. Okay, so let's just say we go with 266 for now because 304 is not on the table. So these numbers will be conservative. So here, for my weak axis buckling, my weak axis buckling effective length is 1 meter because we have the mullions restraining it in the out of the page direction. So that's 782, and in the strong axis direction we have 748. And remember that our applied axial force was 488. So this is more than double. So, or it's not quite double, it's less than double. But remember that we have a square on this term. So if we're using up half of the axial load capacity, only a quarter of it goes into our interaction equation because it's a half times a half. Okay, so these numbers are looking kind of okay. And this might be an okay section to choose. So I'm going to go with that. I'm going to summarize what we just got out of those tables. Should point out as well that the MR in the table assumes that your KL equals 1, right? It assumes that you're not having lateral torsional buckling, which will be the case in this case. Why? Because it's a pretty squarish member. The ratio of depth to width is less than 2.5 to 1. We are going to check that when we do bending. Okay, and the ESI, remember we have to check ESI when we do bending, is 4220 times 10 to the 9 Newton millimeters squared. And ES is equal to E because we are in dry conditions right now. So that is fine. Then our P, our X is 748 kilonewtons. Strong axis. Okay, and the strong axis has a 3 meter length and the weak axis has a 1 meter length. And these values are for the 175 by 266, which is all that was in the table. So, but these are conservative values. Okay, fantastic. So now, how do I find the, so now what I'm going to do is I'm going to actually, before I go any further, before I go and check all these moment resistances and all that stuff, I'm going to check all the moment resistance, shear resistance. I'm going to include consideration of shear notch and all that stuff. What I want to do as a first step here is to just use these values from the table, which are conservative values, like the the axial load values are definitely conservative, the PRX and the PRY, because they're for a slightly smaller beam. And I'm going to plug all these into two of the interaction equations in order to see basically whether I am going to be okay or not before I go any further. Okay, so I haven't actually calculated PR and MR. I'm just going to use the values from the table just to check the axial load and bending interaction equation now, before I do too much effort. Okay, so the first thing that I need, though, is I'm going to need PE, which is my Euler buckling load. Which is like this. And what's my E05? My E05 for glulam is E times 0.87, and that's something that you get from the table 7.3 or table 7.2 if you're in the 19 edition. And I am not going to go to the tables for all of these values explicitly because I'm assuming we've done enough examples now that you can go get these table values yourself, because now is the time that we need to start saving some time since this example is so long. Oh, I never wrote down what the section was. We're going to try 175 by 304. That's what we're doing. And it's a spruce pine 20F-EX. So don't forget that this length on the bottom is actually an LE. And that LE is effective length in the plane of the applied moment. And in this case, the applied moment is in the strong axis direction. And in the strong axis direction, the effective length is the total length of the beam. In the weak axis direction, the out of plane direction, remember, the column is restrained at the points of the mullions, of the window mullions. So then the LE would be only 1,000. So I do this, and I get 4,026 kilonewtons. Okay, so now what I'm going to do is for some of those load combinations, I'm going to just check a couple that I think might be the critical ones. I'm not going to check them all for now. I'll check them all at the end. But here's my summary. The ones I'm going to check are, I'm going to do this one here, 3C, the one that has the highest axial load and a medium amount of moment. And then I think I'll do 4D, which has kind of a medium axial load and a moment that's close to the highest. Okay, you know, I could do 4B, but the axial load's a lot less and the moment is almost the same. So those are the two that I'm going to choose instead of going through and checking them all, because right now I'm just doing a sanity check. Yes, this section looks like it's going to be okay. Okay, so let's do that. So let's start with low case 3C. So just to recall, this is the equation for our interaction for axial compression and bending. Oops. So this is going to be MF over MR 1 over 1 minus PF over PE. So this is why we needed PE, and this has to be less than or equal to 1. Okay, so let's sub in all those values. Our PF, our kind of maximum PF is 447. Now, that's the one from load case 3C. Our PR, and this is going to be for strong axis, is 748. Okay, I take that, I square it. And then my MF for this load case is 17.9. My MR, oh, I forgot I have to multiply this by 1.15. Okay, so this is, what did I say, 748. I have to remember that this is a load case that has KD of 1.15. So I'm going to put 1.15 here. Okay, this is MF, and then MR is, we saw that it's 62.1. Going to also multiply that by 1.15 in order to get the actual load at the right KD. And I'm going to multiply all that by 1 divided by 1 minus 447 divided by PE, which was 4026. And I'm going to calculate that out by hand and show you what each term is. First one is 0.27. So even though, as I mentioned, even though I'm taking up about half of the total strength, I am only taking about 27% of the actual interaction. Now, I won't have to do this 1.15 business later because I'm going to use the actual resistance that I calculate for that load case, which is going to include the KD. But since right now I'm using the table values, those table values don't include the KD of 1.15. That's why I'm including it extra. And then this one here, and this one's going to be about 28%. And these two together are going to be equal to about 55%. So that's fine. I'm less than 1. This term here, in this case, this amplification term caused an amplification in this case around something like 12%. Okay, let's do the same thing for load case 4D, which also has a KD of 1.15. Just going to put a note here. Now, of course, when I multiply this by KD, I'm saying here I'm approximating the effect of KD, right? Because we know that for compression resistance, it's not linearly proportional to KD, not exactly. Okay, so this is definitely an approximation of the actual strength at a KD of 1.15. Okay, again, this is not the final check on load combinations. This is just an initial check to give myself some confidence that I can continue with this design and it's going to work. So this one has a lower strength, a lower compression load and a higher moment. So we're closer to the moment capacity. So less percent of the axial load than before, than the axial load capacity. Oh, I made a bit of a mistake the first time. This is actually, it was 0.17 without the squared. With the squared, it's 0.03. So only 3% actually. And I get 0.58 total. Okay, so both of these are fine. It looks like it might be a bit over conservative in terms of axial and moment interaction. So, I'm only using 60%, but remember that in terms of the shear strength, I am pretty close, right? And that is basically what governed our selection of this member, because that's the shear force and there's the shear strength, and they're pretty close. And that VR does not yet take into account the fact that we have a shear notch cut out of the member. Okay, so I'm going to put a cut in here. And in the next video, we're going to start checking everything for this selection. So basically, at the end here, we're basically saying that our trial section of 175 by 304 seems reasonable. Now do all checks. Okay, and that's what we're going to start doing in the next video, starting with longitudinal shear resistance, since that's the one that we think is the closest is the shear resistance.